Hello and welcome to PEEPanEIP, your go-to source for EIPs and all things in Ethereum. I'm your host Pooja Ranjan, and today we have an exciting episode lined up for you. We are going to deep dive into the world of Ethereum simulation with a focus on client implementation, use case, and toolings available. So whether you are a developer, an enthusiast, or just curious about the inner working of Ethereum, this episode is for you. Welcome back. This is PEEPanEIP episode 135. In next few minutes, we'll explore how ETH Simulate can help you test and validate Ethereum transaction, we'll understand its technical intricacies, and discuss its real-world application. Joining us today are key contributors to ETH Simulate, Oleg, Killari, and the team. Welcome to the show.
Hello, everyone.
Since our listeners are meeting you for the first time here, I would like to kick off this podcast with a brief introduction. If you don't mind sharing about what has been your personal journey in the Ethereum space and how did it lead you to get involved with ETH Simulate?
I can go ahead. I'm Killari, an Ethereum developer. I have been in the space for like 8 years, but I haven't actually been working in the full-time in the Ethereum for that long. I have been working full-time for like 3 years. And out of those 2 years, I have been working in the Dark Forest team. And we are working on the Interceptor browser extension that simulates the transaction that users are making. So we felt that there was a huge need to explain to users why the transactions are made, or if you're making a transaction, what the transaction does. And the ETH Simulate is the way of our browser extension works, so that all the simulation and everything, the core functionality of the Interceptor is the ETH Simulate.
And my name is Oleg, and I'm in Ethereum for last 5 years and was co-developer, I think, for 2 years already, focusing on Nethermind client, its RPCs, and in ETH Simulate, I was doing the main part of its implementation for Nethermind client. So I had a lot of fun with it, touching all the bases like modifying the EVM, modifying the RPC, the overlays for database, and many, many more stuff that we'll talk about today that are crucial for ETH Simulate to actually work.
Very interesting. Thank you so much for introduction. I always think that these background from developers help new people to get on board. They get inspired, and eventually we can have them as Ethereum core contributor one day. I understand there is a presentation, so without further delay, let's peep in.
So we'll be talking about the ETH Simulate V1, which is an execution spec 484, a proposal in the execution API repository. We have been working on this with the Go Ethereum, Nethermind, and the Interceptor team. And I will bit demo or show what Interceptor does with the ETH Simulate to explain what is the purpose of the whole ETH Simulate. So it's an execution spec 484 in the repository, so I recommend everyone to check this repository out and read about the ETH Simulate. It's quite complex method, so there's a lot of details that can be found in this repository or in this pull request. So what the ETH Simulate V1 is basically like ETH call, except it's with more functional than ETH call. So you can perform simulations on the Ethereum mainnet or in all the other chains like ETH call does. But with ETH call, you can just simulate one transaction at once. And with ETH Simulate, you can simulate many transactions together. There's a couple of other ways of doing this, like Alchemy forking methods or Flashbot's ETH call bundle. And the biggest limitation of those are not standardized. So the main purpose of the ETH Simulate would be that it would be included all of the major clients. And at the moment, we are working with the Nethermind and ETH for this. And on the side, you can see example call that you could make to the ETH Simulate. So it's an RPC method. And in this call, I'm setting address balance to some amount. So you can set any account's balance or ETH balance to anything you want. So you can be as rich as you want in the simulation. And after we have set our balance, we can send transactions. So these 2 transactions that are sending ETH around. So one big benefit of ETH Simulate is that you can send transactions from any account. So you don't need to have private keys of any of those accounts that you are sending, and you also can send transaction from the contract that is normally not possible. And when you are performing that call, this is the result that you are going to get. So there's big amount of information that you are getting. So the result is an array of blocks, and here's one block, and we are just simulating one block in this example. And you can see that we are getting 2 calls, and there's 2 return data being returned. So if you are doing ETH call, you are just getting return data. So one field of what we have here is the return data, which you can get with ETH call, but with ETH simulate, you can get way more. For example, there's the logs. So when the transaction is executed, we are also sending the logs. And all the other information is basically block receipt information. So that's also one big difference to other methods that we are simulating blocks and not just transactions or calls. Here's the 4 core features of ETH simulates. So as I mentioned, the calls are split to blocks. So we simulate blocks and not calls or transactions, and we can override block variables to what we want. Then we have state overrides, like you saw that I could set the ETH balance of any account, and we can do that for all of the accounts, and we can also set code or other variables to what we want. Then there's ECRecover opcode override. Nowadays, huge amount of things that users are signing are actually messages and not transactions. So it's very important that we should be able to know what users should be able to understand what kind of messages they're signing, and the simulation is one way to do that. And in the ETH simulate, we can override ECRecover to do exactly that. Then we have also event logs. So as I said, ETH call doesn't return logs of those transactions that you are sending. And so we thought it was very important to return those. And then one big feature is also the ETH transfer logs. So when you are sending transactions, we also produce logs for when you are sending ETH around. And these are the 4 core features that I will then go through one by one. So the calls are split to blocks. So you define blocks, and you can override things in the blocks, and then you can put calls inside them. And the overrides you can set are, for example, block number. So in ETH call, you are simulating all the calls inside the one block that you are defining to be the kind of the root of those calls. So in ETH simulate also you set that, like in this call, you can see that in the very bottom, there's the latest. So this simulation is run on the top of the latest state of the blockchain. And then when you set the number, those can be the higher than that number, higher than the current state. So for example, if the current block is 10, you can simulate the blocks in the like block 100, and then the ETH simulating is actually producing blocks from that 10 to the 100, and then just doing the simulation of your block. Then there's time that can be also overridden. This is really handy if there's some contract that expects it to be executed only after some certain amount of time has passed. So with ETH simulate, you can simulate that kind of scenarios. You can just by setting the time to that amount that is required by the contract, and then just executing that call. Then there's a couple of other fields that you can also set, but I don't think those are that interesting compared to those 2 other things you can set. Then the replace account state is quite interesting, as you can set the balance of any account to be whatever you want. And the more interesting one is the code. So it's when you want to develop a contract, it's very important that you test that contract and how it behaves in the different kind of scenarios. And with the ETH simulate query on the right side, you can see that I'm setting the balance of that one account to a certain amount, and then I'm overriding and add code with something other than actually should be there, and then I can call that contract. So basically, I can deploy a contract without actually deploying it on the mainnet, and then I can call that contract in the mainnet, even though it actually is not there. And this overridden is not limited to some places that don't have code already, but you can override any contract or any address on the chain. So for example, if you want Uniswap contract, you can replace the Uniswap contract with any other code that you want, and then you can call that contract and see what would happen in that kind of situation. And this is really powerful feature, as you can tie out the different kind of things on the chain and then see what happens without actually needing to send that kind of transactions. Then there's state and state diff variables that can also be overridden, so you can replace the state of any contract or account. And then there's move precompile, which is the one that I'm going to talk next. So here's a Solidity contract that I have written that is supposed to be replaced, or I can replace the ECRecover opcode with it. So when you are calling the ETH simulate, you can replace the code, and you can replace also the ECRecover Precompile with any code. So you can replace this code, and then this can spoof the signatures of any messages to be whatever we want. So here's in the first mapping row, we can set that if this contract receives input which is existing in the mapping, then we can replace that call to be the address that we want. And if it doesn't exist, then we are calling in the below, there's the 12356 address being called. So I can move the ECRecover contract to that, which is being called if it doesn't exist in the mapping. And here's the ECRecover side of the things. This may be a bit unclear, but I will show an example on how this is actually working in the practice, and this kind of backend side of the thing of what I'm kind of explaining. So the ECRecover contract exists in the address 1 on the mainnet, and here I'm doing a state override of that contract. So I'm replacing it code with the contract I just said, the Solidity contract, and then I'm moving the precompile of that ECRecover actual code into that 12356 address. And then I'm doing the state of mapping, replacing the mapping state with the one that is shown below there. So you could have seen that in the Solidity contract that I have written, there was no way of setting that mapping contract. And that's not really something that we need to do in the ETH simulate. We can just do a state override. And so we can have a smaller amount of code and then just replace the state of what we want there. And state we are replacing there is the input variables for the ECRecover. And then what I'm saying that match that is signed with is the Vitalik's Ethereum address. So with this, we can spoof with Vitalik's message. We can sign that message by Vitalik, even though we don't have Vitalik's private key. We can just say that it is signed by Vitalik, and the chain just trusts that information. Here's an example how we can see that in the practice. Here's on the right, you can see a screenshot of the interceptor browser extension that I'm working on, and it's highly leveraging the ETH simulate functionality. So in the above there, you can see the simply making rich and easy 20 approval. So this is the interceptor transaction stack or the simulation stack. And when you are sending a transaction in the interceptor, it is making a simulation stack transaction that are being sent to the ETH simulate, and then it outputs the result of the ETH simulate. And here the simply making rich can be applied in the swap UI, which is the swap that we are using for this example. And you can see in the below the ETH there's balance 200,000. So the ETH simulate is setting our ETH balance to that high, and we can then observe different applications in the different kind of simulation scenarios. And here we want to swap USDC to ETH, and then when we click the swap, the interceptor will pop up and ask that we need to approve this Uniswap permit contract. And then we can click to simulate, and it will put that in the ETH simulate transaction stack and execute it. And after we simulate it, we are getting next pop-up, and then we need to sign a message by the host swap to simulate the permit. So this is not an actually transaction, but it's a message that we need to be signing. And here we are signing with Vitalik address, but we don't clearly have Vitalik's private key, but we can spoof that we have the Vitalik's private key. Then after that is signed, the host swap is asking us to swap USDC for ETH. And then we can just click to simulate, and the swap is successful. Here's actually what's happening in the background. So all those, when we are clicking through the windows, is that we are approving transaction to simulation stack, but we are not actually sending those transactions. We are just creating a transaction stack to be sent to the ETH simulate. So there's the first call is the approved transaction that we did, and then there's the permit message, which is just the ECRecover override that we just did, and then we can perform the swap transaction. And what the swap transaction does in the background is it calling the ECRecover precompile in the background, and then it's calling it with that hash that we have there. It's notice that it's actually signed by the Vitalik, and it approves that swap goes through. And after that, the interceptor can show that we have received some kind of ETH, and we have lost some amount of USDC. And then we have been also allowing the Uniswap permit to through contract to spend USDC. And how we can get this outcome is that these are actually logs that I'm aggregating together. And which goes to the final big feature of ETH simulate is that when you're performing ETH simulate, it's producing event logs and ETH transfer logs. Below you can see Uniswap ETH to VBTC swap, and we can see all things that are happening in the swap. This is just the simulation. We don't need to have to send the transaction or anything. And then we can see that the 5 ETH is going from the Vitalik's address, that 3F address, and the 3F address is then wrapping that ETH, and then the wrapped ETH is then moving further in the chain, and finally we are getting VBTC to our Vitalik's account. And this is something that you cannot really do simulation with the ETH call, since we are not getting the event logs, and then ETH transfer logs is something that are not normally there, but we have made them so that you can enable this feature to track ETH transfers that are happening in the chain. So when you enable the feature, with your logs, you are also getting the ETH transfer logs, which look exactly like ERC20 transfer logs, except the address is coming from the 0xE address. So this is a special address that we have chosen that indicates that this is an ETH transfer log. And then everything else in this log are exactly like what happened in the ERC20 transfer. Then there's one other example where I show that how you can leverage the replacing the code of any contract on the chain. So governance Bravo is a very widely used governance contract on the chain. And the idea is that you have some governance DAO that is wanting to make some kind of governance proposal, and someone has made a proposal with some text description that I want to send this amount of ETH for this person because they're doing some kind of work, and then there's a bytecode that's going to be executed if the governance approve that kind of transaction. And there have been that kind of cases in the past where the description of the proposal has not really actually matched the transaction that's been sent, and that has even happened in the cases where the person who made the proposal actually made the wrong bytecode that is being executed, and then the ETH being sent went to the wrong address. That wasn't the intention. And with the ETH simulate, we can do that. We just replace the time block contract with the new contract, and here's the Solidity contract that I have written, which is basically just the governor admin time block contract that has removed some kind of access rights things so that anyone can call it. And then with the ETH simulate, we can also know that what kind of stuff is happening when we do that override. So on the left side, you can see the input for the ETH simulate. So there's the code, time block contract replacement bytecode. So there's one contract that I'm just replacing the code that is there, and then I'm just executing that contract. And then I'm getting the input. So if this is the governance contract execution, then I can know what does the proposal actually does. And for example, you can see that there's a log with address for the ETH, so the 0xE transfer. So we know this execution is moving ETH, and then we can dive more into the simulation trace to see that where the ETH is being moved. So then all the people who are voting for that governance contract could do this kind of simulation, and then they actually could see that the description of the proposal is actually corresponding to what is happening on the chain or should be happening on the chain. There's two existing implementation of the ETH simulate at the moment. There's the Nethermind version, and Oleg is going to explain next part on how it was actually implemented on the Nethermind. And then we have also Get implementation, which is developed by Sina, who is also on the call. And we are also asking people to more implementation for it. So our idea for this ETH simulate to be standardized with all the clients. And at the moment, we have been working with just the 2 clients to get it to implement on these clients.
All right, and now let's talk a little bit about implementation details that we came up with while doing our implementation of ETH simulate at Nethermind. Let's go to the next slide. So in simplified form, you can imagine ETH simulate as a machine that would allow you to take your general blockchain tree and make branches out of it. Many branches wherever users might want to go to explore what can happen on the chain, what can happen to contracts if certain decisions were made. So to actually implement it, our code allows users to take any parent block they want, as it's called us. We take that block, if it is on the node, we take its header, we take user desired state updates, for example, for contracts, for user balances, for any account changes that are wanted. And then we also take user overloads for precompiles and stuff like that. We compose block headers, And then for each of the transactions that user provided for the block, we simulated from the state that we got after we took our parent block and updated it with desired state updates. So we compose a real block, and then we process it. We process it as close to the way that normal blocks are processed on chain as possible. So while ETH call for it, it would be enough to use, for example, transaction processing and stick with it. For this, we are actually using the same pipeline that is used for block processing. So in our case, they were a little bit different. And so it was a little bit more heavy machinery that was actually working on top of each block, a little bit more of checks and possibilities that are given to the user while they're processing not a single transaction, but a block as a whole. Then when the block is processed, we commit a state update, and that state update comes around to the new block that a user could have provided to us. A user could have provided us, for example, only block number 1 and block number 100. And then for the intermediate block, we'll keep the committed state, create a new block, update its timings, update every detail that would be needed for a block to be like moved on the chain. And then when we'll come to the block number 100, we will use its state, and from it we'll create a real block with transactions, we process it, we commit it, and then we return a traced result to our user. So this is the general way of how each simulation is running. So you can imagine like branches growing out from the tree, and all the branches are of course stale, they are not persistent in memory, they would disappear as soon as the ETH call has finished, but in general one could imagine it like a tree. So let's go to the next slide, please. And here you can see all the major aspects of our client we had to touch to actually implement ECRecover. First of all, we needed to take all of the access to the DBs that we had for the code, for the state, for the blocks, and on top of it, all the blocks that were not persisted onto memory. So, for example, we had a lot of caching, a lot of blocks that were appearing only on RAM before they would be actually committed, and we also needed to take them into our regards. And on top of that all, we needed to create overlays that would allow us to read all the data and actually allow to write from the transactions and from the blocks data onto that overlay layers, so that the original like real data won't be touched, won't be affected in any way. Also, of course, concurrency mechanisms come into play, and you need to make it all safe for the user to not corrupt his database of a node. Then there were updates to actual EVM, because we needed precompile redirects, precompile overloads, and events to the ETH transfer whenever it happens, notifiable and monitorable by us. So we needed to actually change EVM a little bit. In our case, it appeared so that our machinery was not sufficient for complete JSON parsing for the structures and data types that were utilized in ECRecover. So we actually had to also update our JSON parsing mechanisms. And of course, we needed to create mechanism to pre-fill transactions, pre-fill blocks, make it so that if a user would want to input only the meat of the transaction and like no information from the block, this ECRecover call would still work. And all the details the user emitted will be popped up, and the simulation would try to go as completely and as fluent as possible. So let's go to the next slide, please. And first of all, the state updates. We allow state updates of the contracts and of the users. And for us, it actually resulted in a lot of overlaying on top of our database structures, on top of our caching structures. And in real life application, if you already have ETH call with state overrides, you are halfway there, because that state override would actually allow you to update contract and update user state. And basically to that, you would add ability to overload the contract code and overload the precompiles, and you'll be good to go. But basically, it is a lot of overlays, and if you have up-to-date ETH call, it would be easier for you to start with. So let's go to the next slide, please. So for the database, structure roughly looked like you could see on the picture, we had our database that were persistent, database that is in cache, in temporary memory, and from them we got our state, our blocks, and on top of all of them, we needed to create overlays that would be fed into our virtual machine that would actually be able to write into them, read from them the updated temporary state. And this is how you can imagine this branch actually like grows out from our tree, because it is all the simulated stuff, many blocks of potential transactions that can be quite involved and can create a lot of state updates and create a lot of data, basically think is on chain. And of course, we had our block processors that would had to take in mind that they're actually working with overlays and not with real deal. With this, let's go to the next slide. So EVM updates were touching mainly two things. First of all, we needed to, through an EVM update, to allow us to redirect precompile access. So basically, if we are given some code that shall be executed instead of this given precompile, or if a user wants to take this precompile and redirect it to some other address he wants to call later, we needed to allow this functionality. And basically this redirection of precompiles is one of the biggest changes to EVM we had to make. After that, basically a transaction calls for some code, that code calls for a precompile, and if precompile is redirected, we are not using the precompile code, but we are utilizing the code that was provided to us as an alternative, and the contract still thinks it was calling the original precompile call. So with this, let's go to the next slide and look a little bit into logs. So for logging, we actually needed to add to our EVM caches for the cases where ETH is actually transferred, so that it will be reported to our tracer every time, and our tracer would be able to actually do decisions on adding event logs to the resulted transaction, so that the transaction would always show, if a user wanted, and specify that transfers happened, and this or that transfer happened at this or that time, and so the user can then operate with that information in mind. So it touches traces, EVM implementation, and allows us to emit extra event logs. So with this, let's go next slide, please. And our RPC updates mainly included the thing that is a little bit rare on the Ethereum RPC side. Normally, you would generally see plain data types coming in. The most complicated one would be state overrides in current ETH call. But this method, ECSimulate, actually takes a complicated object that can be quite deeply nested into itself, and it would have a lot of fields, like you can imagine, every block, every transaction, every state override dictionary. The states were quite complicated, so this is an object that is passed to our RPC method, and this is quite a bit of distinction from the other potential RPC methods that you might have. Also, with this method comes a new limit variable, basically, that a node can set a limit on the maximum amount of blocks a user can simulate in a row. So as we, due to decisions, need to simulate each block, you can imagine that if user gives you blocks number 0, blocks to blocks number 1000, we would need to actually simulate every block in this pathway. And so it could be a potential DDoS vector that we actually existed through this configuration variable that allows us to actually hard limit on the amount of blocks that you emulate. Let's go to the next slide, please. Also, we created a validation mode in this RPC. So typically in ETH call, you would get nitty-gritty transaction that could not pass validation quite often, and it would be still processed and you will still get some results. But in ECSimulate, we actually allowed validation on mode that would take your transaction, take the parameters that you inputted for your transaction, take your block and parameters for it, and actually do every piece of validation that happens to a real block on a real chain. So if you had 10 blocks, for each one of those, we will process them as if they were blocks that actually are arriving onto chain, so that they shall be checked for every nook and cranny, for the gas to be enough, for the users to have enough gas, and enough ether to process the transaction, and all of the stuff that you would actually need for real transactions and real blocks to be landed. So this validation mode on is some big distinction in terms of how one could compare ETHCall to ETHSimulate, because with ETHSimulate, with this validation mode on, you would actually be able to see what kind of blocks potentially have a good potential of landing or not. Let's go to the next slide, please. And yeah, skipping blocks is often desired thingy. So you would sometimes want to simulate block number 1 and then block number 1000 or 100, and your logic of a smart contract that you are trying to interact with may be dependent on a block number or a timestamp. So we encourage users to actually utilize timestamps for cheaper simulations, because with them you could simulate block number 1 and then block number 2, but state that block number 2 happened like in a year or so. And thus you can bypass this issue of actually like it being hard to simulate 1000 blocks if you just use timestamps instead of block numbers. But for block numbers, for block number enthusiasts, we have this limit on the block, that's blocks that are simulated on a node, and you can of course expand that limit for whatever choosing you might have. So with this, let's go next to the next slide. And we've got great development support from Killari's team, and we've got more than 100 Hive tests that are testing various aspects of what can actually happen on this like subchain that is growing from our tree. You can imagine various situations that shall go wrong, shall go right, shall be interconnected with one another. And this was a blast to work with the team and to actually run these Hive tests that are interesting, that are complicated, and greatly like test your application from all around with various types of requests that can actually happen in ETHSimulate. And ETHSimulate is diverse because basically it is like building a subchain from the chain that you already have. All right, let's go next. And yeah, ETHSimulate overall would allow you to do experiments on a chain that are like a logical evolution of what you had in ETHCall, where you had a single transaction. Here you have blocks, a set of blocks that can be tested. You can use it for MEV research. You can see how AMMs react to whatever conditions you are trying to test them with. You can overload precompiles and see how it would be if a user X signs a transaction B on a contract C. And you can do it all without grave consequences on a thing that would actually emulate the real mainnet, and not any test scenario or testnet that you might have. So with this, I thank you all, and let's go to the last slide. Yeah, we will encourage you to take a look at our proposal. Let's build a nice tree with us. Let's build a simulated tree with all the options that we can have and we can explore on the blockchain in the block space and time. Thank you all.
Thank you. This was a great presentation. We covered the purpose, technical overview, implementation, and application. And I think the pictorial representation of the working of the block simulation was very helpful. We talked about state updates, EVM updates, examples of precompile override. These seems to be very useful feature and maybe implemented in Ethereum clients. And having 100 plus Hive tests, that was commendable. I always love to hear supports on testing because I think that is one of the areas where all developers need support. So thank you, Killari and team, for supporting with so many Hive tests. I would request people to maybe drop their question on the chat if there are any, and we can take one by one. I already see one question here. Sina, if you would like to maybe relay the question for the guest here.
Yeah, my question is to Oleg, and it's basically, what was the trickiest feature or part of ETHSimulate for you to implement?
I think the trickiest feature was the integration with the EVM. And as our EVM is quite large and the code in it is always hot path all the way, it is not that like complicated, but extremely impactful whenever you do any change to it. And thus, to change EVM, to do the change so that it would be minimal, was a great effort where Lukasz helped me quite a lot. And it was, I think, the hardest part. And for you, Sina, as you are the main implementer currently of ECRecover for the Geth client, what was your biggest feature that was like most interesting for you to implement in ECRecover?
I think it would have to be the so-called phantom blocks. So for context, ECRecover had a concept of phantom blocks. These were the blocks that user does not specify and are supposed to be skipped. And we just computed some blocks. We assumed that there were some blocks in the middle between, like in the gap of the chain. And we had to compute some things for specifically the hash of those blocks, because as you might know, there's a block hash opcode that can read the previous 256 block hashes. So if one of those was a phantom block, we would need to produce some kind of arbitrary block hash for it. And somehow this was quite tricky for me to get right, to have like to produce hashes for actual blocks and phantom blocks and keep them somehow. But yeah, so glad that we moved on from that, and like we have actually a different process for generating empty blocks instead.
Yeah, just execute them all. So we got the next question with how much ECRecover would be impacted by a workload, and potentially I would add from myself light clients. So I think it would be really great when you have a light client that you would be able to do all the simulation that Killari showed in the beginning, where you could get your like current state from it. You can do a simulation of what would happen if you actually sign this transaction. And if the contract does anything malicious to you as a like light client user, you would immediately see that you would be scammed. And so this would actually potentially help quite a lot, I think, with danger aversion and stuff like that.
For light client, we have been thinking of having that kind of method that when you perform the ECRecover, it would return all the proofs of all the ECRecover simulation as well. But that's something that we haven't went ahead and started implementing yet. But it's just an idea that we could add the light client support for it as well.
Very well. Thank you so much. I suppose this is okay to consider the primary target audience here for each simulate proposal is the Ethereum client teams, because we already see the implementation in Nethermind and Geth. I'm trying to understand here, is there any EIP in progress for each simulate, and do you have any plans for buy-in from execution clients?
We first considered that we should make it an EIP, but then we decided that execution spec is where all the RPC methods reside. So we thought that the execution spec repository is the kind of the right place for this to reside, and not EIP repository.
Yeah, basically this changes nothing in the client and Ethereum structure. This is only a way to access the facilities that are currently in any given client. So EIP would be too much complication, while this is like just an RPC, but a complicated one.
Sounds good. Of course, EIP has its process and it may increase complication or complexities for developers to get them implemented. I hope that this is easier with just the specs available. I was trying to understand here, like, how are we sharing the specs? Definitely there is no EIP. Are we just trying to make use of the GitHub repository that you have shared in the beginning? Or is there any other way of sharing this with each of the clients team here?
We are intending to share the execution spec for that.
Sounds good to me. Okay, I think we already talked about the biggest challenge on Nethermind versus Geth client. Is there any notable difference in the implementation on these clients?
Yeah, of course. Currently, our client, the Nethermind one, is more object-oriented. So everything there is like a chain of objects that are connected or inherited from one another. And Geth does it a little bit differently. And so the challenges, I think, were quite different and diverse between the clients. But the main result is to follow the spec. The spec is quite detailed. So when you have a spec on your hands, it is like quite easy to get to the same point. But we can say that for now, at least, we have cases when on validation mode on, we allowed ourselves to have inconsistencies on the hash that is generated after transactions are processed on Geth and Nethermind clients respectively. So there can be a little bit differences in that parts of implementations that are like hard to nitpick and pin down, and thus make it like exactly same on both nodes. Yes, Sina, please.
Yeah, I would like to add that because the results of ETH simulate basically returns the hash of the block that we produce locally, the client produced locally, it will be very easy to catch any differences in implementation across clients. Because if one of the clients behaves even slightly differently to another one, then the hash that is produced will be different. This is similar to how mainnet works. And so it has helped us a lot in testing to know when there is difference between the clients and to go ahead and fix that.
Very interesting. I look forward to the implementation in all other execution clients and try to understand, maybe share with the smart contract developers the basic difference so they can pick up for their respective applications. Talking about application, I noticed there was a mention of Interceptor, a project that is presently using this feature. How easy would you say it is to integrate ETH Simulate with existing Ethereum-based projects?
I would say quite easy. We have been trying to make the ETH Simulate output to be very similar to the other methods. For example, the block receipts are about the same like when we are getting ETH block receipt, they should look similar. And the same with the ETH logs are just ERC20 transfer logs. Many of the libraries can process those already. It's just the difference is there is that the address is just the special address, but otherwise they are just the ERC20 logs. Many of other output that we have is planned to be as similar as the other RPC methods are doing. I guess one big difference is that we have added the version number so that this is the ETH Simulate version 1. And the intention with this is that we probably when this get wider used, then the plan is that this method is never going to be modified except for bug fixes, but then we make a version 2 at some point. So if you implement this version of the spec in your library, then you should expect it to work like that in the future as well.
Very interesting. I'm just trying to understand here if you or the entire team may be aware of any other project that is using this feature right now, or if not, then maybe if you can share some of the real world use cases that smart contractors may look into.
At the moment, I'm not aware of anyone else using the method. I said a couple of use cases like what the Interceptor is doing, that you can do different kind of simulations and on the mainnet state, for example, if you are developing a smart contract and you want to test the smart contract right on the mainnet, you can just deploy it in the ETH Simulate. So you can set any contract code to be your code, and then you can just call it and see how it can interact with the other contract on the mainnet. So you don't necessarily have to have a testnet do stuff, or you don't have to deploy it anyway. And then you can also set up some new accounts on the mainnet that have huge amount of ETH, and those can also call your contract and test it. This is one of the many use cases that we have. Basically, all the places that are using ETH call could start using ETH Simulate this bit heavier method, but it maybe can do some other stuff kind of lighter. Like for example, if you are sending ETH and you want to check with ETH call if it went to the right place, you have to make balance checks, and those are more heavy to do than just checking the ETH transfer logs.
And there was mention of MEV use cases as well, like, people may be able to use. So that would be an interesting thing to follow in future.
Yeah, as you can see the reactions of contracts through time, you can actually see how your flash loan would affect the markets, how flash loans specified on a series of blocks would actually perform, and how the MMMs would react. For example, you can play on arbitrage and stuff like that. So basically research how mainnet contracts exist and how they would react, starting from the conditions of the mainnet and prolonging its life into the future that you want to emulate.
Very well. Thank you for sharing that. Let's talk a little bit about the future plans. Are there any upcoming features or update that you are excited about? How do you see ETH Simulate evolving in next few years?
At the moment we are not looking for any new features. We are just planning to get this standardized on all the clients. We had a huge amount of ideas on what we can add to the ETH simulate, but for us it has been really important that we can get this implemented and all of the clients, that all the clients would return the same results. So for example, with ETH call, when you are making ETH call in the different clients, you are getting a bit different kind of replies. And we have been really wanting that with ETH simulate, you are getting the same input on all of the clients. So when wallets or applications are querying the chain, they could expect that to get the same results. But yeah, we have had huge amount of ideas and huge amount of things that in the ETH simulate that have been there, but then removed, but then thought that maybe it could be useful to have that in the future. I, for example, would be interested in having that when you are making ETH simulate and you are deploying contract in your transactions, that you would know what kind of contracts that you were deployed. And at the moment, you cannot get that kind of information. But then again, there's a lot of things that a lot of people want to be included, but they have been trying to cut all the bit less more important stuff away. The light client example, for example, was something that I would want, that you could perform a ETH simulate and then get all the proofs required for the light client to verify that simulation. And that would also be really cool to have in the future.
Yeah, and one can imagine that as this feature would be implemented by primary Ethereum clients, it would be also adopted on L2s. So its use there would be also quite interesting.
Of course, adoption on L1 client first is the primary objective. And if we see adoption on L2, that would be another real gain for us. Thank you. We are coming towards the end of this conversation here for today. Maybe you would like to take this opportunity to share a message to the community and let them know how to get involved.
I think the best way would be to go into the execution specs 4.4 to read about it. And then we have also Telegram group for the implementers, so that if you want to be implemented and getting more involved, then contact any of us and you can get into our group to discuss about it.
Or soon you will be just able to take, or just now you can take master branch on Nethermind client, compile it, run it as a node, and you'll get good to go access to ECRecover. You can play around with it directly, and it will be probably in the next release.
Very interesting. And I see that if we can perhaps have some community-driven initiative to maybe collaborate and associate with the development team and community would be nice to have. Maybe with some bounties, some features, and some contributors in general will be nice to have on board. Any message for the community or anything you would like to share about this particular feature that we hope Ethereum clients to adopt soon?
There are so many possibilities because you can try out it for your day-to-day applications or try it out for like future concepts that you want to play around with to explore how chain reacts. And I see Lucas raises his hand.
Yes, so the message is that we are eager to see more people start using it for their use cases. We are eager to hear, do they find any issues or does it work as expected? And do they miss any new features? So maybe we can work on that and add something if needed. So we are very open to feedback.
That sounds pretty interesting. Thank you for sharing. Well, a big thank you to Sina, Oleg, Lucas, and everyone joining here. Thank you, Killari, for support with a lot of test cases, and the entire team for sharing their expertise and experiences with us today. Thank you, dear listeners and followers, for tuning in to this non-EIP special episode on PEEPanEIP podcast. We hope you enjoyed the deep dive into ETH Simulate and gained valuable insights on how this can be implemented on clients and potentially used for new application. If you would like to learn more about ETH Simulate or get involved, be sure to check out the links and resources in the show notes. And don't forget to subscribe to our podcast on your favorite platform. Follow us on Twitter at ETHCatHerders for latest updates and discussion. And if you have any questions on this topic or you would want us to cover any other specific topic in future episodes, please feel free to reach out. Until next time, keep innovating and exploring this exciting world of Ethereum with Ethereum Cat Herders. This is Pooja Ranjan signing off. Stay safe and keep building.